moving straight on from previous session, so let's let bracket alpha beta be z, this complex number, right? So therefore the sigma squared of A product, sigma squared A, sigma squared of B is greater or equal to 1 over, the square of 1 over 2i looking at the previous sigma squared A, sigma squared B from the previous session is greater or equal to the square of the modulus of the bracket alpha beta. Yeah, I've skipped a line. Okay, now we're letting z, or z, Americans say z, Canadians, British say z, Australians say z, whatever. Okay, so so sigma squared A, sigma squared B is greater or equal to the square of the modulus of bracket alpha beta. So let z be alpha beta. So therefore this is greater or equal to the square of z squared. Sorry, the square of z, the square of the absolute of z, and that in turn was greater or equal to this expression where this is z and that's z star. Okay. Now remember, if you star this, you just reverse the bracket, becomes, the AB swap around, so you get BA. So this BA here is the star of this. Okay. Now, but what is bracket of alpha beta? Well, from one session previously, we defined alpha as a hat minus the average of psi, and beta, similarly, but with b. Now, this term here, we're talking quantum mechanics, right? We're talking operators of corresponding to the observables, the operators in the eigen equation. These operators are Hermitian. Remember, talked about that at length. So that means that you can take this term over to here. You can bring it here. Now you can do that with Hermitian operators. You can flip them back and forth between the bra and the ket. Okay? So bring it over to here. So now you've got, this vertical bar here is now here. Now you've got this term here on the right hand side of the bar, in a sense. It's now part of the ket. Okay. Well, we can multiply it out. So just get 4 terms as you multiply this out. So you multiply these two, you'll get a hat b hat. So you multiply these two, you get minus a hat average b. You multiply these terms, so you get b hat or minus b hat average a. And then you multiply these terms, so minus minus plus average a average b. Okay, so these 4 terms. All right. Now rearrange these 4 terms in the following way. So use, so you'll get a hat b hat psi from here, and the average value, that's just a number, right? It's just a number, so you can take it outside the bracket. So that's what you're doing here. So then you're left with psi a hat psi. Okay, for this term. Similar story for here. A hat's just a number, so it comes outside. So you get bra psi b hat psi. Right? And for this one, these are both just numbers. They're just average values. Okay, so both of those come outside the bra here, and you'll be left with bracket of psi psi. Okay. Alright, now rearranging terms. What is this? That's just the average of A hat, the expectation value. So you can rewrite this as average of B times average of A. So this is this. Similar story here, so minus A hat, minus average of A times average of B. So you get this. And let's assume our wave functions are normalized. Okay, so this will just be 1. So you just live with plus average A, average B. But here you got minus average A, average B. So these two cancel, and you're just left with this term. All right. Now, what we did here was for alpha beta. Now we could go through just the same thing and get a similar expression for the bracket beta alpha. Right? In fact, you just substitute, these are all dummies in a sense. And I could put B here, and wherever's alpha I got beta, and so on. You get a very similar expression like this. Okay. Now why do we want beta alpha? Well, for here. So we've just found an expression for bracket alpha beta, which is this. But we want this term as well, because we want to know what our uncertainty formula will end up as. So we need to know what this is as well. So beta A, and you do this kind of analysis again, and you get this. Okay, so now find the difference between bracket alpha beta and beta alpha, and you will get this expression minus this expression. Now these two cancel, and you're just left with this minus this, right? Here it is here. And you can rewrite that more fully with wave functions and brackets. So this expression becomes this expression. So you'll have A hat B hat minus B hat A hat in the middle here, bracket psi psi. Now you've seen this before. A hat B hat minus B hat A hat. That's the definition of the commutator. This, right, with the square brackets. If you see this commutator symbol, you know what it means is it's just shorthand for this, right? A hat B hat minus B hat A hat. So now it's all inside these angular brackets. So we're talking the average value of, the expectation value of the expectation value of the commutator of these two operators, A and B. Right? Well, there it is. So therefore, I'm going to go way back up. So the variance of A times the variance of B here, okay, is greater or equal to 1 over 2i here of this, the whole thing all squared. Okay, so bracket alpha beta minus bracket beta alpha, which is this, is just this. Right? So plug that into here, and you end up with this expression. And that, you can't see it, but that was the result we were looking for. Okay, so we've got it. So I didn't put it, but we're at the end of the proof, so I could put this. Right? The usual modern mathematical symbol saying that you have come to the end of the proof. Right? One of the things I'm trying to get you guys to become equally familiar, equally fluent in speaking two languages of pure mathematics and mathematical physics, because the two have already merged for the last 2 decades or so. At the highest ends of both these fields, they have become the same field. I talk about mathics, mathematical physics to some extent. So that's the future. Now, probably most of, I'm just guessing, but most of you following me now, probably at undergrad level, if that. So I'm expecting, as I move further and further into graduate level, the distribution of my audience, if you like, followers, students, whatever, will change, become more graduate type. So so for those of you who are following me, who do intend to go from studying the undergrad stuff to graduate level stuff, higher and higher, 4 levels of graduate study, M1, M2, so first year masters, second year masters, and then PhD 1 and 2, first year PhD level and second year PhD level. So it definitely gets a lot harder. So for those of you who follow me all the way through, I would very much like to see you become equally fluent in both, because that's the future of the field. It's not just a personal whim on my part. I strongly see, well, it's not really my personal opinion, it's just a fact that at the top levels, pure math and math physics have merged. They are now pretty much the same subject. Alright, so hence, get familiar with using math type symbols within physics, especially into proof sites. Okay, now, so we have a general formula here now. This is the formula for the generalized Heisenberg uncertainty principle. It's valid for any 2 incompatible observables, A and D. So now you already know about the usual standard undergrad textbook type example of Heisenberg's uncertainty principle, and that's between the position and the momentum. Well, actually, strictly speaking, if you're talking one dimension, the position along the x-axis and the x-axis or direction component of the momentum. So p of x. So it's between x and p of x. You have this uncertainty relationship. So here it is in general. Now let's actually take that and derive from it the usual Heisenberg uncertainty principle, HUP, between x and p. Well, x component of p. Right? So to do that, now these 2 operators, so x hat, that's your position operator,